Yes.
Okay. Shall I start?
Yeah.
Okay, well, thank you very much for the invitation to talk here and for the organization of this amazing workshop. I'd also like to start by thanking all my collaborators. Well, this is a subsection of the collaborators that'll be working on these sections of papers in here. So I'd like to talk about some type of effective field theories that may be useful for cosmology. It doesn't necessarily even need to be for cosmology. It can just be for particle physics. Just as an example, we can ask ourselves what dark energy is. I'm not going to be talking per se about dark energy, but that's just as an example. And I guess 13 years ago now, I gave a summer school and I tried at the time of classifying the different type of models or theories that people have come up with in trying to understand what dark energy is and how it can address the cosmological constant problem. And then I tried to do the same thing just a few years ago. And the number of models has increased remarkably, and that was in 2018. If I were to draw the same type of diagram now, that would be even more impressive. And I have to say, if your favorite model for dark energy or for tackling the cosmological constant problem is not present there, don't be offended. This is very biased. This is not to be taken too seriously. This is just representative to the fact that we have our favorite castle in the sky. We have our favorite model for what we're like the nature of reality to represent. But the truth of the matter is that the community as a whole, including all of us, I mean that as a positive thing, is definitely not lacking creativity in coming up with fantastic models that come closer and closer to the description of the observations that we are having today. And so the aim of the game is, in parallel as coming up with realistic models, is to try to discriminate between all of them so as to get closer and closer to what could explain the various features that we see in cosmology or in particle physics and how all of this fits in together. So there's many different type of diagnoses that the community is imposing on ourselves to segregate between different classes of models. The first step typically is whether or not the model makes sense classically, quantum mechanically, if it's natural. There's a lot of notion of stability that comes in there, but not only. And in parallel, there's also, of course, the complementarity with observations. We want the models to fit the current data and have predictions for future data. And it's not just one set of data. There's such a beautiful multitude of observations and experiments that are present that it's really very hard nowadays to just come up with a new model that will fit all of that. I mean, as we know, GR is working extremely well. And then any type of modifications typically leads to some signature, which most of the time will be ruled out already in some of the observations. So this type of diagnosis are currently going on, and they are typically criteria that can be applied directly at the level of the low energy effective field theory in the sense of the model that is there to describe the universe as we see it today. The type of constraint that are complementary to those ones that I'd like to talk more about today are those which rely on understanding how the models we have could be embedded within a high energy completion and a sensible high energy completion. So I'm going to want to remain relatively agnostic on the precise high energy completion that this model may have. In particular, we don't really want to impose a particular field content or a particular type of way this is going to be, for instance, Higgs mechanism at high energy or anything like that. All we want to have is a high energy completion. So it can be string theory, it can be whatever you want for at high energy. All we want is for this high energy completion to satisfy some set of criteria that we enjoy, that we think makes sense. And you may want to drop some of those, but these are the ones that we're going to keep for today. We like it to be local, this should have been highlighted, unitary, Lorentz invariant, and what I'll focus most of all today is causal. We want causality to be present for our theory as a whole, and this should be present at high energy and cascade down to conditions within our low energy world, within our models that describe the nature of reality as we see it today in a universe or in a particle physics community. So more precisely, the questions I'm gonna like to ask myself is, within a low energy theory that includes gravity, so a gravitational effective field theory. So this is relevant, for instance, for inflation, dark energy, dark matter. It's up to you to decide how low energy you want it to be, but below some quantum theory of gravity, let's say. And it doesn't necessarily need to be gravity playing a major role. You can have beyond the standard model physics as well, but ultimately all of those theories are going to be gravitational, embedded in a gravitational world. And so within those low energy effective field theories, which are gravitational, this precise question I'd like to ask myself today, but this is embedded in a bigger question, is what is the speed of gravity? In particular, can gravitational waves in principle be superluminal, even if we don't observe that? Could other species, for instance, light, be superluminal? And by superluminal, I mean with respect to its speed at very high frequency. And if they can, how is that consistent with causality, and how is that consistent with a standard high energy completion? So when it comes to gravitational waves, I know the immediate answer is, well, maybe that's a theoretical question, but observation tells us that the speed of gravitational waves is 1 to an incredible accuracy. And of course, the experts are in the audience, so who am I to say otherwise? Of course, that is the case. We know from the direct detection of neutron star gravitational waves and light that the speed of gravitational waves to that of light is the same in 1 part to 10 to the 15 or 10 to the 16. I should say that other frequencies of light observed, it's really huge frequencies for light, the speed of light is 1 to, I mean, you can take into account the structure, you can take into account the expansion, you can take into account even the mass of the photon if you wanted to, the lower bound on the upper, the lower bound on the mass of the photon, sorry, the upper bound on the mass of the photon. You can take all of this into account. At those frequencies, the speed of light is 1 to a much better precision. So really, this is a constraint directly on the speed of gravitational waves, which we know has to be 1 in 10 to the minus 15 at frequencies observed by LIGO. And many models of dark energy in the bubble picture that I mentioned before typically predict a non-minimal sound speed for gravitational waves at low frequencies, at least at frequencies of LIGOs or so, by an amount which can in principle be larger than 10 to the minus 15. And that can be either because there's some interaction between gravitational waves, between the tensor modes and dark energy along the line of propagation, or because this model of dark energy really disguise our models of modified gravity. And we've seen some of those before by the beautiful talk of Chinji. And so don't take this too seriously. Don't get offended if I just put in grace some part of the models which are still consistent with those observations. Don't take that too seriously. It's just as a way to illustrate the fact that those observations are doing an amazing job at segregating already between various models which are consistent with that particular observation, for instance. However, when it comes to the dark energy of EFT, if that's what we're interested in, for instance, they are typically effective field theories which are valid or that are designed to be valid at extremely low frequencies. And many of them, particularly the ones which implement a Weinstein mechanism, will end up having some type of breaking which of the effective field theory, which is at extremely low energy, at actually low cutoff. And then the way this effective field theory gets embedded at high energy is very, very non-trivial. And it can be kind of a dramatic transition between what's going on here and what's going on at higher frequencies. And so it's not inconceivable that for many, or some, let me just say some of these models of dark energy, which are low energy effective field theories, the speed of gravitational waves could depart from 1. I should say this is not 0 here, it should still be small, a small departure from 1 at low frequencies while recovering very close to 1 speed of gravitational waves at frequencies observed by LIGO. And the fact that it will go back to being precisely luminal, this is not an accident. This is just the fact that those theories typically would be implemented, embedded within a Lorentz invariant fundamental theory. And the fact that we seem to be observing at a speed which departs from 1 at low energy is just coming from the spontaneous breaking of Lorentz invariance from the cosmology, for instance. So this is a spontaneous breaking, but at high energy, the wave should be insensitive to this spontaneous breaking. So this is the framework in which I like to ask the question. Imagine that at some frequencies we can conceive even to have a speed of gravitational waves which is not exactly 1, even though at LIGO frequencies they are constrained to be that. What I like to push further is to ask whether it's even a possibility to ask for this positive value in the difference between the speed of gravitational waves and that of luminality, like that of light at very high frequency. Or if we should simply impose that the speed of gravitational waves should be smaller than 1 or equal to 1 as a prior from the outset. And if we did that, then maybe it will simplify a lot of the way we analyze some of our data. And I'll show a graph about that later on in this talk. So before I go into that, into how this fits in with data, let me try to understand why we typically think that having superluminality is related to acausality and why we typically dismiss it from the outset, as we should in any non-gravitational effective field theory. So in any non-gravitational effective field theory, if I have a high energy completion, no matter what it is, no matter what the field content is, it can be some realization of string theory, it can be anything else that you want, so long as it's unitary, Lorentz invariant, causal, and local. And I should say here, if it's non-gravitational, let me start with that, then we can deduce that the speed of all field at low energy, even on backgrounds that spontaneously break Lorentz invariance, should be subluminal. And the way this proof goes is going through some notion of positivity bounds. So typically we go straight from here, from causality to subluminality. This is correct in non-gravitational effective field theories, but it's useful to understand why it is correct and how the notion of positivity bounds come into this notion. So I'll discuss a little bit about these positivity bounds and try to understand how they really capture the information on the dialogue that goes between the high energy completion and the causality of the high energy completion and the low energy effective field theory that we're interested in. Because after all, if we're just interested in a low energy effective field theory, there's a decoupling of scale between what's going on at high energy and what's going on to low energy. Just like the sound castle, I don't need to know about the structure of the sound to be able to do my sound castle. There's a decoupling of scale. But still, I like to argue that there's a communication or there's a cascade down of some part of the information between the high energy and the low energy. And so for this, it's useful to consider the scattering amplitude. We define a scattering amplitude within the field at low energy. So if you want to think of your dark energy field or your inflaton field or whatever field you want to consider in your theory, you can consider some scattering amplitude. I'll look at elastic ones. S here represents the center of mass energy square, and T is the momentum transfer. So think of it roughly as the angle for the scattering amplitude. Now, this scattering amplitude is tended to analytically continue it in the complex S-plane. And we know that we have pores related to the presence of particles, and then we have a branch cut related to loops of the low energy fields, if there's any, and then the high energy fields that haven't been included in this effective field theory that come in after the cutoff. Now, the very notion of causality is related to the communication between what's going on at low energy. So this is our region of validity of a low energy effective field theory. And we like to have some criteria at high energy. This is where we impose locality, for instance. We have some notion of a UV completion that satisfies some set of criteria. And so the communication that goes in between the high energy completion and the low energy completion is directly dictated from the notion of causality, which is encoded by the requirement of analyticity. So it is the analyticity which allows you to analytically continue the scattering amplitude at high energy, wherever it is. So you want to think of it here at high energy, but in the complex plane, to what's going on at low energy. And this notion of causality is embedded in analyticity, so we can continue what's going on, some relation of the amplitude between what's going on here and what's going on there. And so with this in mind, plus the notion of unitarity, which is embedded in the optical theorem that tells you that the imaginary part of the amplitude has to be positive everywhere in the branch cut all the way to infinity, plus analyticity, and then locality and Lorentz invariance tell you that you can relate the positivity of the amplitude in here to some relation for the amplitude within the regime of validity of your low energy effective field theory, and demanding that the second derivative of the amplitude at t0, t was representing the scattering angle, has to be positive definite for this theory to be unitary, to be embedded within a unitary Lorentz invariant, and I haven't written it down, but also causal and local high energy completion. So this is how for any non-gravitational effective field theory, there's a direct dialogue, that is a direct way this notion of consistent high energy completion, in particular causality, is related to positivity bound. And then this is related to subliminality of all the fields, or fluctuations of all the fields about any background, even if it spontaneously breaks Lorentz invariance. So we can look at that for a standard scalar field. This is a standard example where that works out very well. I have, let's say, partial high energy completion. So I have a theory with a scalar field phi and then another field h here, and they have some interactions. Here, for this theory to be unitary, I need, for instance, the coupling constant alpha here to be positive. And now I'm gonna cascade down to a low energy effective field theory by integrating out my heavy field of mass m down, and the effect of this heavy field within the low energy effective field theory can be captured by new contact term, for instance, like that. And if the theory at high energy is unitary, if alpha here is real, then the coefficient here of those operator has to be positive, alpha square has to be positive. And what it means in terms of the scattering amplitude, you can look at it here. This will lead to a positive second derivative of the scattering amplitude. And in terms of looking at the speed of fluctuations about any background that spontaneously breaks Lorentz invariant. So this theory here doesn't break Lorentz invariance, but it admits some vacua that may spontaneously break Lorentz invariance. And the speed of the fluctuations about them is subliminal if this alpha squared is positive. And at low energy, if you just had this theory, you could just ask for the derivative of the scattering amplitude to be positive, and that would require that this alpha squared has to be positive. So it all seems to make sense within this scalar field theory. So there's a direct relation between the sign of this coefficient here, the sign of the second derivative of the amplitude at t is 0, and the fact that the fluctuations are always subliminal. And I took the example of a time breaking symmetry. You can do something about space like field, and that would be the same thing exactly. So it will always be subliminal. So in a non-gravitational effective field theory, there is relation between causality and subliminality via the positivity bounds. And this is illustrated in this particular example. Now we want to do the same thing for gravitational effective field theory. And this is very, for many reasons, it's much more subtle. So it's much more subtle for various reasons. Just the connection to the improved positive bounds, or the positive bounds themselves and subliminality themselves are more subtle, and this is what I'm going to focus on. And then there's a whole layer of subtleties, which we can discuss all day about, on whether even at high energies, there's a direct connection between causality and analyticity, whether we should really require locality when we have gravity. All of those are questions and I'm gonna put on myself. These are very interesting questions, but even being as minimalistic as possible, as optimistic, let me say, as possible, and keeping a high energy completion that satisfies this requirement, particularly satisfies analyticity, the notion of positivity bounds and the notion of subliminality is far less obvious in gravitational effective field theories. Even if you're not interested in gravity per se, even if you're just interested in dark energy field, for instance, the fact that it's embedded in a gravitational framework does affect what we mean by these requirements. And so there's two reasons for that. The first one, which I'll discuss first, but I'll be brief about that, thank you, is about the gravitational exchange. And then the second one, which for us will have a bigger impact, although it's a little bit more trivial, so it'll be easier to explain, is because of frame artifacts that comes in as soon as we're dealing with gravity. And we've seen some of these effects in the previous talks very nicely explained. So let me start with the first one, the gravitational exchange. I'll be brief here, just to say that if you're considering a scattering amplitude of whatever species you want to have, it can be fermions, it can be the electron, for instance, if you're interested in whatever particle physics. As soon as you embed this theory in a gravitational framework, as you should, everybody will do ultimately, you can't prevent from also generating a gravitational exchange in this process. And this gravitational exchange comes in with a pole related to the fact that we have a massless particle in the game here, namely the graviton, which is a spin 2 massless particle. And so that leads to a contribution to the amplitude that is not analytic at T0. And so that compromises the applicability of these positivity bounds. So the positivity bounds themselves are not strictly applicable because of this gravitational exchange in a gravitational effective field theory, even if you're not interested in gravity per se. So the failure of this applicability is related to the fact that we have gravity, of course, and so it's related to the Planck scale. If you send the Planck scale to infinity, there's no issue. And so what it means in practice is, while for non-gravitational effective field theory, you have some positivity bounds, which is related to a subliminal speed, and so causality imposes subliminal speeds. In gravitational effective field theories, we don't need to have absolute positivity of the coefficients in the scattering amplitude, the coefficient of this S square, for instance, because of the T-channel pole. You can have some small level of negativity, which is suppressed by the Planck square, but still is present. And so in practice, what it means for the sound speed is that it doesn't need to be exactly subliminal. You can allow for yourself a small level of subliminality so long as it's sufficiently suppressed by the Planck scale. And so in gravitational effective field theory, be it for gravitational waves, being for light or anything like that, as soon as you include gravitational effect, you can have a small amount of what you consider being qualified typically as small amount of subliminality, and it's not in contradiction with causality, so long as this level of subliminality is not macroscopic. It's a very small amount. And then the effect, the support outside the light cone will not be physical. Okay, so yes, so because I don't have much time, this has some impacts in how we separate between different effective field theories. And so some effective field theories that we consider, it has been done in the past that we look at the coefficients of the operators, and then we look at various backgrounds. And if we have some type of subliminalities about any background, we say that this theory makes no sense, and we put some constraints on those operators. This is typically what has been done and still being done a lot of the time. And the argument I like to make is this is not in contradiction with causality, and a small level of subliminality of this form for gravitational waves, for instance, on FRW, on Schwarzschild metric of this form, is not in tension with causality and should not be used as a criteria to discard some of these operators in the low energy effective field theory for gravity, and you can do the same thing for other effective field theories. Now, for the last maybe 1 minute that I have, I'd like to talk quickly about frame artifacts, which in practice has also an effect in what it is how we want to constrain our effective field theories, even though in principle this is a completely trivial artifact. So let's go back to the example we considered before we had it without gravity. Without gravity, we made the claim that there was this coefficient here had to be positive so that the fluctuations of this field were subliminal, and this was related to causality and a standard high energy completion. Now, let's imagine we did the same thing with gravity. After all, this seems to make sense. And so the fluctuations of this field would be subliminal as compared to the speed of light or the speed of gravitational waves. But nothing prevents me from performing a frame transformation and going to now Jordan frame, where the field itself is canonical, but I have some new interactions for gravity itself. And then this type of interactions for gravity means that gravitational waves themselves will no longer be luminal, and the scalar field itself will be subluminal. And so clearly here, there's no contradiction, there's no tension with causality with having gravitational waves being superluminal. It's just a gauge artifact, and it's not at all intentional with causality. And this has some relevance when we're trying to put some constraints on low energy effective field theory. And so the simple message I want to claim, is that in case of doubt, or in any time, imposing strict subluminality on the speed of gravitational waves is not in connection with causality, because the speed is something which is gauge dependent, whereas causality is not. And so the cleanest framework to impose the notion of causality in any case of doubt is to simply impose the approximate positivity bounds, which allow a level of negativity from the T-channel pole in these gravitational effective field theories. And so this is just an illustrative example of what happens when we do it for a particular example of dark energy. This is a quartic Henri model with some given parameters. Don't worry too much about that. And so in yellow are constraints from observations. In purples is the typical type of constraints we would have imposed on ourselves by asking for subluminality, which one may think is related to causality, but actually the requirement from causality are what is written in black and are quite different. And so that can have quite an impact in the way we put priors on our cosmological data, for instance. Okay, so sorry for taking so much time. Let me stop here. We know from observation that the speed of gravitational waves is very close to unity. However, I like to understand what's going on at very low frequencies, or I like to understand whether in principle even we could have some small level of superluminality, which is smaller than that. And this is relevant when putting constraints on any type of effective field theories. So our claim is that gravitational waves may be superluminal, and that's not in tension with causality, so long as we're very careful the amount of superluminality that we allow for ourselves. And so typically in a frame where matter and gravity can decouple, so putting aside the frame artifacts, we can allow ourselves for a small amount of superluminality of this form. Thank you.
Thank you very much, Claudia. We have a question from Luke.
Hello, Claudia.
Hi.
Thanks for the nice talk. The observational evidence that the speed of gravity is 1 also is evidence for the strong version of the equivalence principle, because the gravitational waves are accelerated in the field of large-scale structure, of our Milky Way, of the host, the source galaxy, and so on. So my question is, when you tune your theory so that the speed of gravity is 1, are you automatically sure that the strong version of the equivalence principle will be satisfied? Namely, if I am in the freely falling frame near nearby mass, and I perform say Cavendish experiment in this frame, a gravitational experiment in this frame to measure the gravitational constant, for instance, am I sure that the value will be the same as if I repeat the experiment very far away from external masses?
So, I mean, are you thinking structure or something like that? I mean, it depends a little bit on the energy scales, right? So the reason why you may have a departure from the speed of 1 at all is either due to the presence of the dark energy field that breaks some level of the equivalence principle. And so this is typically this is typically consistent with observations if there's some type of screening mechanism that comes back in the game. So that may be a Weinstein mechanism or anything like that. So typically this is working very well, although it's hard to look at it in precise context because of the way this screening mechanism is implemented. But it depends a little bit on the energy scales you're considering. So if you tell me, again which precise situation you have in mind, we can discuss about it. But the issue typically with this type of model is to look for constraints or for signatures in other type of systems. So they're doing pretty well at screening themselves. So this is if one would have a tiny departure of the speed of gravitational waves due to the presence of another field that breaks the equivalence principle. If you have it because of a more severe modification of gravity, let me just say modified gravity or anything like that, then typically this modification is at such a low energy scale that in any of the system that you like to see it coming, the effect is extremely small. So you see no departure from it.
Okay, thank you. So indeed, the equivalence principle, the strong equivalence principle may be satisfied at some energy scale, typical the scales that are compatible with the observation of gravitational waves and so on. But there may be still a violation at high energy or.
So typically in those systems, unless we start invoking all the layers of physics, once it's satisfied at a given energy scale, then it will be satisfied at high energy scales. So the modification really comes in at lower energy scales, typically. I mean, it's not quite as simple because of course the symmetry or all sorts of other factors come in, but roughly speaking, the more massive, the more energetic, the faster a system is, the more likely, the closer to GR it's going to end up being.
Okay, thank you.
Yeah. So the problem we have with a lot of these models now is that we really need to go to huge cosmological scales to see any departure at all, because things look so much like GR in all of the other system that put a constraint, and then we have to go to very, very low energy, very large distances to be able to see any departure, typically.
Okay, thank you very much.
Okay, thanks a lot, Claudia. I suggest that if there are other questions you can ask on Gather during the coffee break. We can join on Gather and we can keep discussing. Let's